So I'm Sharon True, and I'm joined today by Francis Quek in the audience, and he might join me for questions. We're from the Department of Visualization at Texas A&M University, and unfortunately my colleagues from the Department of Psychology could not join us today. So there has been great interest in to use making to support learning and education in both public imagination and in research. And indeed, much research in making for learning has shown that using making results in a very rich and multisensorial experience for children. Our own work, published in 2016, has shown that the hands-on nature of making helps learning to be more exciting and more interesting for children. But most making studies of this sort tend to be qualitative in nature. And to be exact, 52% of them, according to a survey of the literature published in 2016. And furthermore, these studies tend to be conducted in settings such as workshops and camps, which allow for the study of certain kinds of variables like enjoyment and interest, but not other kinds of variables. And in our work, we were interested to investigate variables that focus on the development of the person, of the child. And more specifically, we were interested in the development of identity and children's learning. And the study of these kinds of variables require a more sustained and longer-term study. So in our work, we asked three research questions. So first, can making activities integrated in formal schooling influence elementary or primary school students' sense of self-efficacy in making, interest in making, and sense of identity as makers? Second, can making activities in formal schooling influence students' sense of science self-efficacy, interest in science, and intended career paths in science? And third, can student participation in curriculum-integrated making activities influence students' academic performance in science? So the work that we talk about today is part of a larger scale project that's called Making the Maker. And in that project, we integrate making activities throughout the school year in elementary school, intervening in 2 classes of each of 3rd, 4th, and 5th grades, essentially with children aged 8 to 11 years old. So in total, we have 121 students participating in our making intervention, and we track those students throughout the whole academic school year. So the school that we are working, the elementary school that we're working with, has a student populations, and those students who come largely from underrepresented groups. So 72% of those students are from Hispanic or Latino background, 26% from African American background, and only 2% white or Asian. And 96% of their students are on reduced lunch programs, and over 50% of those students have English as a second language. So we're from Texas. In the state of Texas, the elementary school schedule is broken up into 2 semesters of 18 weeks. So these 18-week semester are further broken up into 3 segments of 6 weeks each, and each 6-week segment covers 1 science topic or 1 science unit. Each week of the school semester covers a set of mastery goals or specific learning objectives that the teacher has to cover. And we intervene in the science classroom 1 week out of every science unit. So essentially, we cover all the science units and across 1 week throughout the whole school year. In total, across all the 3 grades, we intervene 18 maker weeks across the academic year. So to enable this study, we developed a series of maker kits that's aligned with the curriculum or the mastery goals, the learning goals of the week in question here. So the maker kits were developed by our team, which consisted of computer scientists, engineers, designers, people from the School of Education, in collaboration with teachers from the school where we work with and in the classes where we were going to intervene. So from our point of view, making is spearheaded by 3 main set of technology. First, digital fabrication, open source electronics, and third, programming. In this first year of the project, we focus on the first 2, digital fabrication and open source electronics, and all our kits in that first year use those 2 mainly. So here's one example of the food chain kit where the students has to learn about the flow of energy. Essentially that energy is produced by the sun and energy is transferred from producers to consumers and decomposers. So the students would build the circuits and then arrange the organisms into the correct order and then light up LEDs across to show the transfer of energy. here you can see it. The second example here is the earthquake kit, where the children has to learn about volcanic eruptions. So the fact that volcanic eruptions consist of rapid changes in the Earth's surface, and that can result in damages of the natural built environment. So the children will build the electronic circuits and attach that to vibrating motors that's attached to foam core boards. And these foam core boards represent tectonic plates that vibrate with the motors, and eventually they separate, simulating an earthquake, and the children's houses would collapse. And understanding that there's a rapid change that's happening in the Earth. And here's a third example that's called the human body kit. And in this example, the children has to learn that the production of energy requires both oxygen and sugar obtained from food. So when the respiration circuit is activated, the lungs, symbolized by a pulsing LED, work. Activating the eating circuit alone, however, does not produce energy, but both the respiration and eating circuits together need to be activated for sugar to be metabolized and energy to be produced. So to make that clearer, let me show you a video that was produced by a local TV station that shows the children demonstrating the kits in an open house that was covered by the media at the end of the year.
They might be small scientists, but their unique projects are anything but small on a few levels. Students at Neal Elementary in Bryan have teamed up with Texas A&M.
The goal is hands-on invention and children in science, technology, engineering, and mathematics. News 3's Brooke Wellborn shows us the impact this program is having on the students and teachers.
When Dad plays things to the bottom,
I get to work with circuits.
Angel Salinas says that's been his favorite part about teaming up with the colleges at Texas A&M. It's helping him and others develop skills in science, technology, engineering, and math. The hope is to keep kids engaged in these subjects now so they keep working in them and further their education.
I want to become an engineer.
It's really exciting to see it actually happen in the classroom. I see a lot of my students who maybe wouldn't normally be interested in science or in math or in reading. They actually are engaged.
This collaboration has been in the works for nearly a year and is part of a $1 million grant from the National Science Foundation.
Each year our partnerships grow more and more and more with Texas A&M, and this grant that we're using with Texas A&M, it's 2 more years. So we're going to continue to see even better technology, even better science projects.
A&M students and professors visit the Neal Elementary students every 6 weeks.
Makers Lab will come for a week of our instruction, and then we will do the same exact lessons that we would normally do during class time, but we also incorporate the making activities in hopes that the lessons are more engaging.
Anything from cup robots to homemade earthquakes is what the students have put together during their lessons. And the instructors working with them say they're seeing how their learning is progressing.
We're already seeing some indication that they are thinking of themselves more positively as possible scientists. There are more responses to our questions as to what you want to be when you grow up.
At Texas A&M, Brooke Wellborn, News 3.
All right. So that was our little local news coverage. So again, if you remember from our research questions, we were interested in forming longer-term variables. So self-efficacy, interest, identity that we evaluated through the idea of possible self and career interest, and performance in science. So we conducted 2 types of tests on the scores collected through questionnaires and survey forms that we administered to students at the beginning of the year and at the end of the year. So in the first test, we look at the making scores collected from the making classes at the end of the year versus scores collected from control classes that did not participate in our making intervention at the end of the year. And in our second test, we compared the scores collected at the beginning of the year and the post scores collected at the end of the year for only the making classes, the students have participated in our making intervention. So I will quickly highlight the significant differences that we saw here, but don't worry if you miss the numbers because I will summarize all the effects in the model that we're proposing afterwards. So for making variables, we saw significant differences on making self-efficacy and making interest. Comparing making classes versus control classes, there were no significant differences at all for making classes in terms of pre and post scores. For science variables, we found significant differences on science self-efficacy, science interest, and interest in STEM career, looking at making versus control classes. And for pre versus post-test, post-course tests, we saw significant differences in terms of science self-efficacy, STEM possible self, and interest in STEM career. In terms of academic performance or test scores, we did not find any significant differences between making versus control. What we did find that the test scores, and these were state examination scores at the end of the year, that they were correlated with maker possible self, science self-efficacy, and science interest. So what does that actually mean if we summarize all of these effects? So we proposed this model that our making intervention contributed to increases in making self-efficacy and interest, but not necessarily to making identity. There was a very positive, significant trend towards making identity, although we did not see a significant difference in our study. Our making intervention contributed to increases in science self-efficacy and science and identity, but it was more unclear on science interest, and we suspect that there could have been a ceiling effect there. There was no significant effects on test scores, but there were correlation between test scores and science self-efficacy and science identity, as well as on science interest and maker identity. It's also useful to note that all the making variables were correlated with the science variables here. So to simplify this quite complex model, let me put it in a different way. We can say that classroom making did not contribute directly to state science test scores in science, but classroom making may potentially affect test scores indirectly through the mediating path of science variables. So we see science self-efficacy here and science identity, and these science variables are correlated with making variables of interest and self-efficacy. We also asked the students about their career choices, the first and second career choices at the beginning of the year and at the end of the year. We took all these career choices and coded them based on whether it was related to STEM or not related to STEM. So these are some examples of careers that we get. For STEM careers, we get careers like biologist, geologist, robotics engineer, game developer. For non-STEM careers, you get examples of policeman, firefighter, football player, working in fast food, truck driver, or being president. Why not? So looking at the percentage of STEM careers here, we see that at the beginning of the year in our maker classes, it was only at 4.82%. At the end of the year, that number increased to 19.54%. That means that many more students wanted as a first choice career to be doing something related to STEM. Compared to our control classes, that at the end of the year, that number of STEM-related careers was still at 2.22%. The same positive effect was seen on their second career choices. In the second career choices at the beginning of the year, STEM-related career choices were only at 13.4%, and that increased to 19.10% in post-test. And compared to control classes, which stayed at 9.09% at the end of the year for second choice STEM careers. So in conclusion, what I would like to point out here are four main things. So first is that making may increase self-efficacy leading towards identity, but not interest. And that may seem curious for some of you, but it does make sense if you think about it. So let me use an example that was talked about in Blickstein's work, where he had students make keychains. So students making keychains over a long period of time may lead to them feeling more confident about them being able to make keychains. So the increase in self-efficacy, and perhaps even them feeling that they may potentially be keychain makers, the effect on identity, but not necessarily leading to the students being interested in the topic of keychains itself. So that might be an explanation for our results here. Secondly, making may move career choices towards STEM, and we've seen that in our first choice career choices that we asked the students, for many of them. But even for those students who did not move to a STEM-related career choice at the end of the year, making may expand the scope of possibilities in STEM careers, as we've seen in our second career choices. So what that means is that a child might say at the beginning of the year that, hey, I want to be a basketball player. And at the end of the year, they might still say, yeah, as my first choice, I still want to be a basketball player. But if I can't be a basketball player, I could be a scientist as backup plan. So now, at the end of the year, they feel that there's toolkit has expanded in scope, versus at the beginning of the day, they couldn't even imagine themselves to be able to do that. It's a career that's related to STEM. And my last point here that I want you all to take away is that making may contribute to academic achievement in science, but not necessarily to direct ways. So we did not find direct effects or correlations at all with test scores based on our making intervention. But there was an indirect path by which making affected test scores, and that was through the path of science variables and maker identity. And why through maker identity and not through, say, maker interest or self-efficacy? That, again, is a little bit curious. So our possible explanation for that is that we measured maker identities through seeing how much the children had maker-related traits, such as resilience, perseverance, or experimentation. And these, we think, are generalizable enough traits that could affect their test scores when they're taking tests in science, but not necessarily their interest in science or self-efficacy, the interest in making or the self-efficacy in making itself. So in our current work, we are moving now to integrating programming in our maker kits. So we are just about to wrap up our second year of the project, and we are hoping that these same trends and the model that we propose would be maintained. And with that, thank you very much, and we are open to any questions.
Hi.
Hello.
Danielle Wild, University of Southern Denmark. I have a question about the way you're framing whether you want to be a scientist or not. I've been running biohacking courses, essentially biohacking the entire high school science curriculum for 10 weeks at 2 local high schools. And what we found is that if we explain to them that it doesn't matter what you want to do, science moving forward becomes integral to it, it opens up a very different kind of conversation. So science is not seen as something separate from doing anything, just about. And I'm curious about the results that we got were radically different from the results that you got. And I think that there's something about this that's key to it. And I'm curious if you reflected on the choice to position science as something that, as opposed to not science, as you know, science is something clearly distinct that can be put in a box, as opposed to something that takes place in many different disciplines. And I just wondered if you had any thoughts on that.
So I think you have to think about the population of students that we're dealing with. Okay, many